Hey everyone, Monic the Shooter here, and today we're going to be going over AB Physics 2 material with atomic physics. Well, I guess it's called modern physics, but we'll be going on atomic and nuclear physics. So I have two practice FRQs here for AP test, but these also are common questions you'll be asked in class. Um, so this is a atomic physics FRQ, and this is a nuclear, and this will kind of help you. These are the kind of two FRQs you'll get in on the AP test. So let's get started into it. Let's zoom in here. So the figure shows energy level diagram for hypothetical simple atom. The wavelength of the radiation emitted when electron undergoes transition B is 400 nanometers, and for transition C is 700 nanometers. Calculate the wavelength of the radiation emitted when the electron makes transition A. So we have B, we have C, but we need A. And one thing you might be tempted to do is, hey, B and C, let's just add up the wavelength and that's what we'll get. But that's, on first glance, there's a few things that will not be right. Number one, you can just add the wavelength like that. Number two, by adding those wavelengths, you'll get a what? You'll get a 1100 nanometer wavelength. That, I remember, a higher wavelength means a lower energy, and A will have the highest energy drop of these all. So if anything, A should be the lowest wavelength. And then you'd be thinking, okay, well, let's do 700 minus 400. But that's also not right because you cannot, again, you can't just add and subtract wavelengths like that. What you can do though is you can figure out the energy drop for B. So the energy drop for B plus the energy drop for C will be equal to the energy drop, energy release for A. So and using the Broglie hypothesis, we know that E, the energy, is related to wavelength. This isn't de Broglie, but you will use it. HF, and then E is equal to HF over lambda, which is wavelength. So let's get into it. Now let's figure out what we can do. The first thing we need to do is let's figure out the energy for B. So energy of B. And for this, we need to tweak our formula a little bit. So we have the wavelength. So we need to do, what's it called? So we need to do EB is equal to H, like we said, C over 400 times 10 to the negative 9. And this is going to give us an energy of 4.97 times 10 to the negative 19th joules. Okay. You might be tempted to change that into electron volts. I honestly don't think you shouldn't, because we're going to have to go back to joules in a bit either way, so there's no point in doing it. And now we need to calculate EC. So EC is going to be equal to HC over 700 times 10 to the negative 9th. Remember our wavelengths, they're given right here. So, and this is going to give us an energy of 2.84 times 10 to the negative 19th joules, which makes sense. EB, the energy of B is higher than the energy of C because it's making a larger gap. It's jumping a larger distance. So, and it has a smaller wavelength, so it's a higher energy. So what we can do is we can add these two energies up, and that'll be the energy of EA. So we can do EA is then going to be equal to HC over lambda. So then we can do 4.97 times 10 to the negative 19th joules plus 2.84 times 10 to the negative 19th joules. Let me zoom out real quick. Will be equal to HC over lambda. HC are constants, so I honestly don't normally write in the constant values. I know what they are, but if you're wondering real quick, just in case maybe you're not so secure on it, H is Planck's constant at 6.63 times 10 to the negative 34th joules seconds, and then C is the speed of light at 3 times 10 to the 8th meters per second. So yeah, we're gonna solve for lambda right here, and I can tell you right off the bat, this is lambda is going to be somewhere around 255 nanometers, depending on exactly what you do for sig figs. So, and then this is also why we didn't convert these numbers into electron volts earlier, because they would have to be in joules now. So this is our answer for A, 255 nanometers. Okay. So let me erase this all now. In the meantime, I hope you guys are having a great day. Maybe if you're taking AP tests for physics, I hope you're studying hard, because Lord knows I am, or at least trying to. All right, let's go on to B. Calculate the maximum kinetic energy for an electron emitted by the metal. Well, okay. The photon emitted during transition B on is then incident on a metal surface as a work function of that. Calculate the maximum kinetic energy. So this is going to go back to a formula that you would have learned in chapter 27, I think, depending on what book you're using. But that is, the energy of the photon is equal to the max kinetic energy the electron can have plus the work function. So if this is the principle of conservation of energy, because this, if you remember from before, is E equal to HF. So this is the energy. So this is the energy of the photon at first, right? And this is the energy that is required to initially break electrons out of your what's it called, of your shell, and then anything left over, which is this, is what the electron will have. So one thing it's not asking this question, but one thing you'll be asked about sometimes is a cutoff frequency, and your cutoff frequency will be the minimum amount of energy that you need to knock your one electron out with zero kinetic energy. So that would be HF cutoff is equal to just work zero, because your kinetic energy would become nothing. So same principle for if you had the cutoff wavelength, it would be this. But that's not in this question. That's for a different time. But just making sure you should know that. Okay. So we don't have F here, but we do have wavelength. So we can do what's it called? C over 400 times 10 to the negative 9 is equal to our KE plus our work function of 2.46 EVs. And keep in mind, everything here is in joules, so you'll have to turn this to joules. So 2.46 EVs to, should turn that, put this in meters, sorry about that. 2.46 EVs to 1.6 times 10 to the negative 19th electron volts per joule. So in this case, the kinetic energy that we are going to get is going to be, the kinetic energy we're going to get there is going to be equal to 4. I'm sorry about that. I have it written down in the wrong place. Let me just do it real quick for you guys. Just give me 1 second. 6.63 times 10 to the negative 34th times 3 times 10 to the 8th divided by 400 times 10 to the 9th. And that'll be minus 2.46 times 1.6 times 10 to the negative 19. And so sorry about that, guys, your kinetic energy is going to be equal to 1.0365 times 10 to the negative 19th joules. So let me just erase this right here and put that there. Okay, so that's part B. Now we're going to go to part C. Calculate the Broglie wavelength of the ejected electron. And if you remember what the Broglie wavelength is, that is, wavelength is equal to h over momentum. So or in other words, h over mv. So you might be tempted right now to tweak some formulas and make lambda input energy, use this, get it in like lambda, and do something like that. So what that would be looking like is, what's it called? Sorry, this. So HF, and you return energy into HC over lambda, and then solve this for lambda and plug that in. Sorry about that. I don't know why that happened. You'd be tempted to solve this for lambda and plug it in here. I'm just telling you right now, don't do that. You will not get the right answer. I have made that mistake countless times. When it comes to modern physics, do not take shortcuts. It's putting in more numbers in a calculator, yeah, but you will make less mistakes. So let's do this. So what we are going to do here is we do know the mass of an electron. So instead, we're going to use the kinetic energy we just solved for times 10 to the negative 19 joules and just solve for the speed it's going. The mass of an electron is 9.11 times 10 to the negative 31st kilograms, and we're going to solve for v. So the velocity we're going to get is something around the lines of 4.75500 meters per second. And now we're just going to plug that into the Broglie wavelength formula and just do this equal to h over 9.11 times 10 to the negative 31st kilograms times 4.75500 meters per second. And that is going to give you the Broglie wavelength of 1.53 nanometers. Or 1.53 times 10 to the negative 9 meters is 1.53 nanometers. Okay. So just take that in for a second until you do that part. Okay. Okay. So now that's those photons will be emitted. Photons emitted during which transitions A and C, when incident on the metal surface, will also result in electrons being ejected from the metal. So one thing I can tell you is A will for sure do it. A will for sure. Okay. The reason we know is that A has a very high energy get jump, and we know that since transition B ejects photons with kinetic energy, that means transition A has to also. Because transition A is a higher energy. So when we do this, HF is equal to KE plus your work function. This is higher for transition A, which means this will be higher because this is staying constant. We know B does it, so now we just have to see. We just have to check, does C do it? And that will be plugging in to this formula. First of all, we'd even see what the energy produced from this is. So HC over 700 times 10 to the negative 9th. And this will give us in joules. So I'm going to put the whole thing over 1.6 times 10 to the negative 19th just to see what is electron volts and compare it to the work function here. And if this is more than the work function, then we know kinetic energy is going to the electron. Otherwise, if it's less, that means we're not even getting electrons to shoot out. So we're going to see. So 6.63 times 10 to the negative 34th times 3 times 10 to the 8th, right? Then we're going to divide that by 700 times 10 to the negative 9th. And then we're going to divide that by 1.6 times 10 to the negative 19th. And you are going to get 1.77 electron volts, which is less than 2.46 electron volts, which means that C cannot do it, but A can. So right here. And I'm not going to write down my justification, but I'll tell you right now, it's kind of just a worded explanation of what I just said. C's the energy that C releases when it does its energy drop is too low and isn't higher than the work function, which means that no electrons are even being emitted. Versus with A, the highest energy drop of the three, it does release enough energy to knock electrons down with kinetic energy. And that's honestly my explanation. You put that in like a bit fancier words, maybe toss some conservation of energy in there, like explain like how that has to do. And yeah, that's how you would do this one. So these honestly aren't too bad. I would say they're pretty manageable. Now we're going to go over nuclear. So let me just move this over so we have some space to work with. Let me move this here. This is everything that you have right here, you will have on your AP test. I just didn't pull the one from the official AP website on here. So what we have here is an unstable nucleus is initially at rest, decays into a nucleus of fermium 250 containing 100 protons, 150 neutrons, and an alpha particle to the kinetic energy of that. The atomic masses of helium-4 and fermium 252 are that and that respectively. So what is the atomic number of the original unstable nucleus? So that's honestly just a very easy reaction. So we don't know what's being produced on the left, but I mean what's being reacted, the original reactant on the left, but we do know what's on the right, so we can backtrack. So we know it's fermium 252, and fermium is Fm, I'm pretty sure, on the periodic table. I'm fairly certain about that. It's it is Fm. So it's fermium 252 with 100 protons, so it's 252 100 plus an alpha particle, which is just a 4-2 helium. So if we add the atomic numbers, we'll get 256 on the top and then 102. And if we look at what this atomic number corresponds to, that is NO right here. So let me write this. So the atomic number of that is just 102. This is your answer right there. Okay, so what is the velocity of the alpha particle? This is also a pretty straightforward question because they actually gave you the kinetic energy of it. You just have to turn that into joules and then do 1/2 mv squared. So be careful, 8.42 times 10 to the 6th. They give you what the mega, kilo, all these things are on your AP sheet. So it's 8.42 times 10 to the 6th meters per second. Electron volts. Then that's times 1.6 times 10 to the negative 19th joules over electron volts. Sorry. And that's equal to 1/2. And the mass of an alpha particle, keep in mind you have to put it in kilograms. So they give it to you in AMUs, so 4.0026 AMUs. And the conversion to go to kilograms is right here. They'll give this to you. I just round up to 1.67 times 10 to the negative 27th kilograms. And then V squared. And then V is going to come out to, V is going to come out to around 2.01 times 10 to the 7th meters per second. Pretty straightforward. And now C asks us, where does the kinetic energy of the alpha particle come from? So I want you to think about that yourself really quickly. Just see where does it come from? Just think about it. And pause the video, think about it. If you don't know, come back. I'll explain it right now. So hopefully you had some time to think about it. When it comes to nuclear physics and reactions, basically, you have your original nuclei. So all your protons, neutrons, all of those stuff right here in the center, right? I'll cap it in purple. And then it reacts into, and they all kind of are scattered apart, basically. When these are all combined together, they're combined together with something called binding energy. And binding energy is related to mass by Einstein's E equals mc squared. You have some energy, which means you have some mass. So that is what makes, so it's actually, from these equations, it's also plus your binding energy. So when all these protons and neutrons, when the nucleus kind of explodes or goes apart, binding energy is released because now the energy that was once holding it together is gone. And that is what gives us the alpha particle its kinetic energy. So that's that explanation. So let me do this. 2.01 times 10 to the 7th meters per second. Okay. So, I can erase this now. Assuming all the energy released in the form of reaction, assuming all the energy released in the reaction is in the form of kinetic energy of the alpha particle, determine the exact mass in the original unstable nucleus to an accuracy of that. I'm just going to do it in kilograms because you could easily find it in AMU when you have it in kilograms. So I'll show you how to do that. Oh my. technical difficulties sometimes. Okay, so let's do it. So the first thing we need to do is figure out our masses. Since I'm doing it in kilograms right now, I'm going to turn everything in kilograms. So we need to figure out what our products are. So our products are fermium 252, which has a mass of 252.08249, and converting that to 1.67 times 10 to the negative 27. Then we're going to add, I'll just add the alpha particle on this side, our alpha particle, which has a mass of 4.0026 times 1.67 times 10 to the negative 27th. And now we need to add in that binding energy that is going all into the kinetic energy of the alpha particle. So remember, E equals mc squared. What was our kinetic energy? It was 8.42 of that. So we need to convert that into the mass, and that would be mass is equal to E over to c squared. So that's what I'm going to do here. 1.6, I'm sorry, 8.42 times 10 to the 6th, and then times 1.6 times 10 to the negative 19th. Keep in mind this has to be in joules. 3 times 10 to the 8th squared. And now what you are going to do is add this all up, and you are going to get 256.0. Oh, I'm sorry. That's in, I have the AMU one written down next to me too. You're going to have 4.251 times 10 to the negative 25th kilograms. That's how you do that. And if you want to turn that back into AMU, you would use this conversion you have right here. And you would divide it by 1.67 times 10 to the negative 27th kilograms. So, that's how you do that part. And now let's talk about this last part. Suppose that fermium-252 nucleus could undergo decay in which a beta minus particle was produced. How does this affect the atomic number of the nucleus? So, I want you to, think about what beta minus decay is. So let me just write the generic formula for that. That is A, Z, X. That becomes A, Z plus 1, Y. So this is symbolizing your change in elements. Plus your 0, negative 1, beta minus particle. So let's look. What happens to the atomic number? It's actually increasing. So that's honestly exactly what happens. So how it affect when they ask you how it affect the atomic number of the atomic number nucleus of the nucleus increases by 1 because a neutron turns into a proton and releases an electron beta particle. And since there's now one more proton, basically, the atomic number increases by 1. So yeah, I hope this helped you guys learn how to do this a little bit better. And good luck on your AP test. I will catch you guys later.